In the last video, we operationally defined temperature as that thing measured by a thermometer, upgraded the thermometer to a constant volume gas thermometer, and we took a look at defining temperature scales. It then pointed out that with the redefinition of SI, the Kelvin scale has changed, and actually along with that, the definition of temperature, and so we need to work towards that. To that end, need to start with another quantity that's been redefined, the mole. So a mole is just a number. In fact, it's related through Avogadros number. So Avogadros number is defined under the new SI to be exactly 6.022.140.765 times 10 to the 23rd inverse moles. And the inverse mole is just there to make units work out. And this is an exact number. So if you have a mole of bricks, you would have 1 mole times Avogadros number equals this quantity right here, many bricks. And again, this is now an exact number. The old definition of Avogadros numbers is the number of carbon-12 atoms in a 12-gram sample. This is no longer the official definition. So now it is correct to say that if you have a 12-gram sample of carbon-12, the number of atoms you will have is very close to 6.022.140.765 times 10 to the 23rd, but it probably isn't that exactly. But still, the atomic mass unit is still defined to be the mass of a carbon-12 atom over Avogadros number. And so that works out to be 1.6605 times 10 to the negative 27 kilograms. So if you have Avogadros number times the atomic mass unit, that's approximately 1 gram. These used to be exact, but with the redefinition, these are now incredibly close approximate values. But what this means is if you want to know the mass of a mole of some molecule, you can add up its atomic masses to get the molecular mass, swap the U with a G for gram, and you will have basically the molar mass. And to any practical measurement, it's going to pretty much measure out the same, unless people are doing incredibly fussy and super sensitive chemistry. So for a bit of notation here, in the number of moles of something is the number of atoms over Avogadros number. A handy way to remember how this works, so this is the number of moles here. So it's often the case in physics that the lowercase sign is the uppercase sign, in this case the number of atoms or molecules. Divided by something. So that's, at least for me, that's the easy way to remember it. The other thing is that the individual number of particles is going to be a very large number in pretty much any situation, and the corresponding number of moles will be a small number. So big N goes to the big number, small n goes to the small number. So just to make a quick concrete example of that, let's say you have half a mole. So let's just ask, what's the mass of half a mole of carbon dioxide? Well, we can look up the atomic masses. So the mass of 1 mole is going to be, well, the atomic mass of carbon is 12.011 atomic mass units. So the mass of 1 mole of carbon would be 12.011 grams. And the atomic mass of oxygen is 15.9994 atomic mass units. So the mass of 1 mole of oxygen would be 15.9994 grams, except we've got 2 of them for every 1 carbon we have, so we have to times that by 2. But I didn't ask for 1 mole, I asked for half a mole, so we'll divide them all through by 2 to get that it is 22.0049 grams. All right. So with that out of the way, we will segue into discussing ideal gases. So the key assumptions are low density. So this means that molecular interactions will be primarily with the walls of the container. And the temperature is well above the condensation point. And again, this is because we want to avoid atom-on-atom interactions. In this case, if you condense, what will happen is 2 atoms will relatively strongly interact with each other, and then they start moving as one. And this has the effect of effectively removing a particle out of the collection. And since we want to keep the number of particles the same, that's why we need the temperature the same. Now, when we talk about processes going forward, we're always going to have in the back of our mind, and I'll spend more time on it later, what's called the quasi-static process assumption, which for now, we can just say any thermodynamic process we can think about is going to run slowly. And this is because we need the container to have a well-defined temperature and pressure at all times. So for instance, in a gasoline engine, when you ignite the fuel-air mixture, you don't have a well-defined temperature throughout the cylinder. And so that would make it hard for us to talk about the gas as a whole. You would have to use computer simulation. So with that, if our gases are ideal, it means they're subject to the ideal gas law, and we'll do more with that as we go on, which is PV equals NKT. You can say, wait a minute, I remember in chemistry it was nRT. Yeah, you're right. Notice here, this is a big N, this is the number of particles. K is Boltzmann's constant. In the more classic chem version, this is little n, the number of moles, and R is the ideal gas constant. It turns out that physicists will use these two about on a 50-50 split. Now, this is also more stuff that has been redefined with the new SI. So on the way to defining the new definition of temperature, temperature has been redefined, defined through setting Boltzmann's constant. to be an exact number. So Boltzmann's constant is now defined to be exactly 1.380649 times 10 to the negative 23rd joules per Kelvin. And this is an exact number. This does have a knock-on effect. If you remember, little n is big N over Avogadros number. So for everything to work out, the ideal gas constant is Boltzmann's constant times Avogadros number. If you go ahead and work it through, and please don't bother memorizing all these numbers, it's 8.3144626181532 joules per mole Kelvin, and that is exact. So like I say, the Kelvin will be defined implicitly through Boltzmann's constant being set to this exact number. So we're linking the Kelvin, our unit of temperature, to the joule, our unit of energy. Okay, so to work with that a bit more, we would like to take that a bit further. So if you measure the velocity, measure the speed of atoms at particular temperature, and this can be done by using, say, an oven, which has a very small hole in it, so gas molecules will occasionally escape. And then what you can do is you can make sort of like a toothed wheel like this. Then you have another one over here. You put them on a common shaft and you spin it at a known angular velocity. Now you know the distance between these. And so the trick is that the gas molecules can only be going at a very specific speed if they can make it not just through the first slit, but also the second slit. And then you just have a detector over here to count them. So when you do that, you can plot the fraction of molecules that are going at a particular speed. And what you get is it isn't a bell curve. It looks bell curve-ish, but then, looks bell curve-ish, but then it has a long tail like that. This actually gets called the Boltzmann distribution. So if you take a look at gas molecules are moving at all sorts of specific speeds. There will be one particular speed right here, which we will call the RMS speed, which we will get to defining right now, and that's the speed that we use to characterize the whole distribution. We know that it always looks like this distribution, so once we figure out the RMS speed, we can stretch or squash the distribution as is appropriate to fully relate the speeds of all the gas molecules to the percentage of the molecules going at that speed. So here's the issue. So let's say you've got a room full of gas. So, okay, there's a room full of gas. Gas molecules are literally running every which way at pretty much every speed you can imagine. So an important question to think about for a moment is, what is the average velocity of these molecules? Okay, I hope you said 0. Because after all, remember, velocity is a signed quantity. At any given time, basically half of them are going to the right, positive, and half of them are going to the left, negative. Same with up and down, same with in and out. So the average velocity of the molecules is 0, but they sure as heck aren't stationary. So what we would like to do is come up with some sort of a number that we can hang our hat on to say what is a typical speed of these atoms. And the number that the physics community has settled on is what's called the RMS speed. The R stands for root. The M is mean. And the S is square. So the idea is the square root of the average, the mean, of the squares of the velocities. So by squaring everything, you make them all positive numbers. Then you take the average, and then you take the square root to get back to a speed. So VRMS is equal to the square root of the average of the velocities. Remember, a bar means average. So square root of the average of the squares of the velocities. All right, now there are other speeds you can use. If you want the most probable speed, it's a little less than the RMS speed. You can calculate what the 50th percentile speed is and all of that. But it turns out that any other speed you might care about turns out to be just some constant times the RMS speed. And for reasons that'll become apparent in a second, the RMS speed is the one that's the most useful to us. So we tend to go with that, and if we need the others, we can always multiply by the appropriate constants. So now here is where we're going to connect the microscopic to the macroscopic. So we will start by imagining that we have a box, L on a side. And at the moment, we just have one molecule, mass M, moving at some velocity, V initial. Now we know it's going to hit a wall. When it hits a wall, it'll bounce elastically and be going out at some speed V final, and the speed V final has to equal the speed V initial. All right, now from this we can figure out what the pressure in the box is. So we can go and take a look. The molecule here would have felt an impulse in the x direction by the impulse momentum theorem. The change in momentum, which was, since it was mv sub x to the right for the x component, and now it's minus mv sub x going to the left, the change in momentum was minus 2 mv sub x. By Newton's third law, that means that the impulse that the molecule exerted onto the wall be equal and opposite, which is plus 2 mv sub x. And that's, again, like I said, by the impulse momentum theorem, equal to the change in momentum in the x direction. All right. Now, how often is this one molecule going to hit this wall? Well, it's going to be the round trip time. So how often is that going to be? Well, it's going to be the time it takes to make a complete lap sideways back and forth, so the distance is 2L over V sub x. All right. Now with that, we can describe the average force that the molecule exerts on the wall. That'll be by Newton's second law. And again, this is the x component of it. Delta p sub x over delta t. Well, we just worked out delta p sub x is 2 mv sub x. And delta t is 2L over v sub x. So the 2's cancel, and you get mv sub x squared over L. Okay, but this would be equal to the pressure times the area of the wall, PL squared. Now, the thing is, we have more than one molecule. How many of them do we have? N. So let's put in an N to account for the number of molecules. Now, at this point, we have to be careful. When we do this for one molecule, we could just go with V sub x squared. Now we need the average value of V sub x squared. All right. So if I divide both sides through by L squared, I'm going to get an L cubed in the denominator, but L cubed is the volume of the box. So this will be the number of atoms times the mass of each particle over the volume times the average value of V sub x squared. Now, there's absolutely nothing special about the x direction here. If I had done this analysis for the y or z direction, I would have gotten exactly the same thing. We say this is isotropy, which just means it's the same in every direction. So isotropy requires that the average value of Vx squared equal the average value of Vy squared equal the average value of Vz squared. But by the Pythagorean theorem, the average value of V squared, just the square of the velocity, square of the speed, would be equal to the average value of Vx squared plus Vy squared plus Vz squared. But since these are all positive numbers, the average of the sum is equal to the sum of the averages. But they're all the same. So we can conclude Vx squared average is Vy squared average is Vz squared average. So this means I can conclude that the average value of Vx squared is 1/3 the average value of just plain good old V squared. All right, going back to here, oops, major boo-boo right there. That should have said, my bad, P equals. I'm sorry about that. So by P equals Nm over V, Vx squared, then this means that if I multiply this through by V, P times V is equal to Nm, just V squared average over 3. But by the ideal gas law, it's also equal to nkt. All right. So I can go ahead and solve this for the average value of V squared. N's cancel. I get that the average value of V squared is 3kt over m. And to get my RMS speed, I take the square root of both sides. So that equals the square root of 3kt over m. So it turns out that what the temperature does is it tells you on average how fast is a particle going. Okay, so let's follow that through just a little more. The pressure, we said, was Nm over V times Vx squared bar, but that's just V squared bar over 3, right? And we can also come up with an average expression for the average kinetic energy of a particle. That'll be 1/2 m times the average value of V squared. But we worked that out. That's 1/2 m times the square root of 3kt over m squared. So the average kinetic energy of a molecule is, well, let's see, 1/2 m. When I square this, the square root goes away. 3kt over m, cancel, cancel. I get that the average kinetic energy of a particle is 3/2 kt. The thermal energy for an ideal gas, now if it's other kinds of gases, that 3 could be a 5 or some other number, but the average thermal, so the thermal energy of an ideal gas will just be the kinetic energy of all the particles. So it'll be n times the average kinetic energy of one of them, so that'll be 3/2 nkt. And this is the basis of the new SI definition of temperature. It is related to the thermal energy of the particles via Boltzmann's constant. So our current interpretation of temperature is just another way of writing the thermal energy of the sample. Now, in practice, thermometers aren't going away anytime soon, but there are special solid-state integrated circuit devices whose thermodynamic properties are incredibly well understood and for which you can readily measure what their thermal energy is at any given moment. These devices are ultimately what will be used for calibration of thermometers. So just to get some sense of this, let's figure out the average kinetic energy of an argon atom at 300 Kelvin. And while we're at it, what is its RMS speed? Okay. Well, we remember that the average kinetic energy is 3/2 kt. So we'll just start there. It doesn't matter that it was argon, it could be anything. The average kinetic energy of any particle will be 3/2 kt. So we can just plug in 3/2 times 1.68 times 10 to the negative, scroll back, sorry, 1.38 times 10 to the negative 23rd. Sorry, 1.38 there. Joules per Kelvin times 300 Kelvin. Works out to be 6.31 times 10 to the negative 21 joules. All right, so how can I get VRMS? Well, we remember that the average kinetic energy is 1/2 mv squared bar. So v squared bar is going to be 2 times the average kinetic energy over the mass, and VRMS will be the square root of that. Okay, so we can put those things in. We said the average kinetic energy was 6.31 times 10 to the negative 21 joules. And if you look it up, the mass of an argon atom is 6.6339209 kilograms. So this works out to be 433 meters per second. Speed of sound is 343 meters per second, so that sure seems like it's in the ballpark. Alrighty. And so with this, we can go back and revisit our model of thermal interactions and start to think about a heat transfer. So let's say you're going to mix two gases. Now conceptually, if you mix two gases, what we can imagine doing is having a very thin membrane that keeps the atoms physically separated. Let's say this chunk of gas is initially at T1 initial. This is at T2 initial. And let's say T2 initial is colder, just to give us some sense of this. Since the temperature is proportional to the average kinetic energy, what's happening is, on average, these molecules will come into the membrane faster than these molecules will. Every so often they'll hit and collide elastically. And in an elastic collision, the one who's going faster slows down, the one who's going slower speeds up usually. So this guy will leave going slower, this guy will leave going faster. And eventually we will get to the point, so I should say, that the one who with the less energy gains and the one with more energy loses. That would be a more correct statement. And so as these collisions happen, the average kinetic energy of sample 1 will decrease, and the average kinetic energy of sample 2 will increase until they're equal. But at that point, this would be saying that T1 final equals T2 final, because the temperatures are proportional to the average kinetic energies. So this is what's going on with the zeroth law. The atoms interact, the one with more kinetic energy gives to the one with less, and this continues until the average atom in each sample has the same amount of kinetic energy. Alrighty, and with that, I will catch you on the flip side. Have a good one.